Hi, this is Professor Fernandez, and this is video 2 in lesson 24. So here we're going to differentiate logarithmic functions, and you see 3 examples here on the screen from Calculus Simplified. There is a new rule for differentiating, new in the sense that this is the first time we've talked about it in the course, differentiating logarithmic functions. So that's down here. Let me zoom in and just talk about that very briefly. So this theorem is fairly short. It's the rule for differentiating logarithmic functions. It says if you look at the function log base a of x and you want to find its derivative, the answer is 1 over x times ln of a, natural log of a. So as a very quick example, right, what is the derivative of log of x? Remember that when we don't put the base, it is convention that the base is 10. So the derivative here would be 1 over x times ln of the base, so ln of 10. So it really is that straightforward. Clearly, it can get more complicated if we have composite functions or other combinations of functions, and that's part of the point of the examples in this video, but that's just a quick illustration of this logarithmic, of this rule for differentiating logarithms. Okay, so where to start? Let's start over here. This is a product, so we're going to use a product rule, but it only involves ln of x. In other words, not like the other one, for example, down here involves a composite. Okay, so if we're going to differentiate this function f of x, we are going to use the product rule because it's the product of x and ln of x. Product rule says derivative of the first times the second plus the first times the derivative of the second. So this one is a power function, so its derivative is, in this case, 1. It's also y equals x, slope 1 line, times ln of x, plus x times the derivative here of ln of x. So let's think about this. ln of x is log base e of x. So if I want to differentiate that, the rule that we just talked about says the answer is 1 over x times the natural log of the base. In this case, the base is e. And if you remember, ln of e is log base e of e, which is 1. So this is a very special case. So if I go back down here, I'll write it down here as a special case in case we're going to use it later. So if your logarithmic function that you are differentiating is the natural log function, ln of x, the derivative is just 1 over x. This is in some ways parallel to what happened in the previous video. Let me just get the number right here, 24.1, if you want to check that one out. That one was about differentiating exponential functions. And we had this really simple result, the simpler version of just another random exponential function like 4 to the x. When you differentiate e to the x, you get back e to the x. So that was the simpler version of the more complicated exponential derivative rule. A similar thing is happening here. This is the simpler version of the slightly more complicated rule for differentiating a logarithmic function. Okay, going back to the example, we now know that the derivative of ln of x is 1 over x, so that gets put over here. All right, so this is the answer. It is not simplified, but we could and we should, to make life a little easier, in case we want to use this later on for anything. You've seen me throughout this course talk a lot about canceling x's and variables from numerators and denominators, and you have to be a little careful when doing that. In this case, I'm tempted to cancel the x's and claim that the answer is ln of x plus 1. That is, in fact, and I maybe should write it this way to avoid confusion, that is in fact true. And why is it true? Why don't I have to worry about x equals 0? Well, that goes back to the function, right? So question, is x equals 0 in the domain of this function? And the answer is no, because ln of 0 is undefined. So I am totally justified in just canceling this x divided by x, because x equals 0 is not even in the domain of the function. So it's not possible for us to consider that point. And I should have put here on the left-hand side, we're calculating f prime of x. Okay, so we did that example. Let's go down here and try differentiating ln of x squared plus 2. This is a composite function. So like we did in that previous video, 24.1, let's go ahead and derive really quickly the rule for differentiating composite functions. Okay, so if I want to take this derivative, right, let's call h of x the function f of g of x, f of u of x equals log base a of u of x. In other words, f of x here is log base a of x, and f of u of x is log base a of u of x, the thing we want to differentiate, right? And we can come up with a fast rule here for it. We say, oh, h prime of x, I'm going to use the chain rule. This is f prime of u of x times u prime of x. Okay, so f prime of u of x. Well, I need to differentiate f. Here is f. What is its derivative? Well, that's exactly the rule we've been using. So 1 over x times ln of a. So if I then go back over here in the bottom, and I am trying to write out f prime of u of x, well, I just take u of x and I put it in here and then I put it in there. So this is 1 over u of x times ln of a, and then I multiply that by u prime of x. So u prime of x. And that is my rule. So the derivative back here of log base a of u of x is 1 over u of x times ln of a times u prime of x. So that's my rule. We have derived the version of the rule for differentiating logarithms that includes an argument for the logarithm that is more general, not just u of x equals x. One thing I want to say about this rule is that in the way that I've written it, just because this is the way it popped out of the chain rule, it looks a little clunky. So let me rewrite it in a different way that looks a little nicer. There we go. Why does this look nicer? Well, first of all, right, if I am looking at the natural log of a function u of x, remember this means that the hidden base here is e, and because ln of e is 1, the 1 over ln of a here goes away because it becomes 1 over ln of e, which is 1 over 1, which is 1. So you'll notice that, this is really the insight that when I differentiate the natural log or the log of a function, what I end up getting is u prime over u, the derivative of the function over the function. It might be multiplied by 1 over ln of a as long, if the base a is not e, or it might just not, right, if the base a is e. So that's kind of the nicer way to write this rule because it gives you that insight. So let's go off then and apply it to this example. I'm going to move things over, give us some space. Okay, so applying it back to this example over here, this entire function here is u of x, x squared plus 2. So my derivative, h prime of x, is going to be 1 over u of x, 1 over x squared plus 2, times the derivative of u of x, x squared plus 2 prime. And I don't need the 1 over ln of a because we're differentiating, we're in this case down here, we're differentiating the natural log, not the log base 10. Okay, so then continuing here, the derivative of x squared plus 2, that's just 2x divided by x squared plus 2. So that is h prime of x. So again, to emphasize, look at what's happening if I differentiate a log, be that log base e or log base any other. The first thing I do is I divide, I form the reciprocal of u of x. I do 1 over u of x, that's what I did over here, and then I multiply that by the derivative, right? That's what I did here. And then again, if the base is not e, I have to also divide by natural log of the base, but I didn't have to do that here because the base was e. Great, so let's zoom right along and go through the last example in the video. So over here up top, you see example 3.38, and this one says differentiate this function. Very, very similar to what we just did, and that's why it's here. So we can do this one of two ways, and I'll do it both ways just to, again, give you some more practice. The first one, you might recognize from the properties of logs that this is ln of t squared plus 2 to the 1/2, and that 1/2 can be put outside. Right? That's something that you could do using the properties of logs. So in this case, the derivative would be 1/2 times the derivative of this function. And this is exactly the derivative we just did. That ended up being 2t divided by t squared plus 2. So our answer to this new question would be 1/2 of that, or t divided by t squared plus 2. That is probably the fastest way to do this problem. It's certainly kind of not cheating, but subverting some of the work, because we took the work that we did earlier to get that derivative, and we didn't actually calculate it in this example. Number 2, what could we do? We could say, you know what, I didn't recognize that property of logarithms. Don't remember it, or maybe just didn't know that I could use it here. So instead, what I'm going to do is I'm just going to differentiate it as written. Okay. If I do that, then my new u of x, right, is this entire thing. This is now ln of u of t, where this entire thing I've circled is u of t. So what would I get from my derivative? Well, as we learned earlier, it's 1 over u of t times u prime of t. And because the natural log here is base e, we don't have that 1 over ln of e to multiply with. So 1 over u of t here is 1 over square root of t squared plus 2. And then I have to multiply this by the derivative of t squared plus 2. You might be wondering, this looks significantly different from this answer over here. But we should have some faith in these theorems that they are in fact true. And we'll see in a minute that things will simplify to the same answer. Okay, so how do I calculate this derivative? Well, I'm going to give myself a little bit more space for this. This is the derivative of t squared plus 2 to the 1/2. So we're going to use a chain rule here. So I pull down the 2 or the 1/2, evaluate it at the inner function, right, to the negative 1/2, and then multiply it by the derivative of the inner function, which is 2t. Canceling things here, the 2's go away. So I have t, and then minus 1/2 throws it downstairs, t squared plus 2 to the 1/2. And then that makes it, in radical form, the square root of t squared plus 2. So that is the derivative here that then is going to be put back to where it came from over there. So if we continue here the calculation, we have equals 1 over square root of t squared plus 2 times this entire quantity. So t over square root of t squared plus 2. Okay, great. So then, oops, that is, yes, that is correct. And then what do? I multiply down here, and I have the square root of something times the square root of something, so I get that something. So I get t squared plus 2 in the denominator. And you can see that that is exactly what we had gotten before. So we do get this nice simplification to the same answer. So I'll zoom out a little bit here. Again, what I would recommend, having now done both of these methods or approaches to differentiating this particular function, you can see just visually, even though we kind of pulled in what this derivative was from the example we did over here, you can see that the approach on the left is a little simpler, because you really avoid differentiating square roots, and you avoid the algebra of square roots that we had to do in this part over here. You avoid that just by using the properties of logarithms. So this 1/2 comes out front. So the square root kind of becomes a multiplicative factor in this problem. And it just goes along for the ride until the very end, where you have some cancellation. So this is the method. This is the method that I would recommend for differentiating this function in this example. And it speaks to something more general, right? Which is anytime you can use algebra to simplify the function you're working with, it's just going to pay dividends down the road. Whether you're differentiating, whether you are using the function to do something else. So first step I would always recommend in any of these calculus questions is, if you're given the function, the algebraic representation of the function, as opposed to, for example, the graph or something, then see if you can use some algebra to simplify it. Also, the lesson that we learned over here, think about the function itself before you start working with it, because that may tell you some information that will be useful. Over here, remember we said, oh, x cannot be 0 because ln of 0 is undefined. So that helped us simplify this answer over here to something that was a little easier to work with if we needed it for something in the future. Great, thanks for watching.